Hello everyone, I am Shobhande, TA of EE6102. Today, in tutorial 3 of the series Tutorial on ANSYS Maxwell 2D, we will learn a basic simulation. It is a eddy current simulation on transformer with interleaved foil winding. So let us start. So this is the model we have drawn in the last tutorial, that is in tutorial 2. So we will do our simulation on this model only. So first I will copy this project. So the model has been copied. Now uh, as we will do, as we will perform our simulation in eddy current environment, so I need to change it. See here, in within bracket it is written as magnetostatic. So now the solver is set as magnetostatic, which is default. Now we need to change it. For this, click on Maxwell 2D, then solution type, then change to eddy current, press OK. See, it is changed to eddy current. Now you can see here the model is symmetric around y-axis. So only simulation of only one part is sufficient to extract the result. So we will use this symmetry and we will take only one half of the model. So to divide it in two parts and take only one part, first select all the objects. So Control A, then go here in speed, click on speed. See the here you can see one faint blue arrow here. That means this operation will keep the right hand part of the model and it will divide along y-axis. So this operation will divide the whole model along y-axis and keep the right hand part and delete the left hand part. And this can be controlled this way. This is the actually yz vector. If you change it to xy, you can see it is outward the screen. It is, if it is zx, it is the arrow is in upward direction. So for us, it we need to select yz. So this only right hand side part will be kept. So press OK. Only this part is kept and the other part is deleted. Now first we need to assign materials to the objects. So this is core. Come here in material tab, select here, then select edit. This in the search window, write ferrite, ferrite. You can see here ferrite, press OK. So the core is now under ferrite. Now select all the windings, go here, edit, copper. Select copper here, press OK. So all the windings are assigned to copper. Now expand the project window. So for any simulation, we need to specify a boundary. So we'll specify now the boundary. For that, select rectangle here, draw a rectangle outside of the object. Suppose this is our boundary. Change the transparency of boundary for better view. 0.8 maybe. Yeah. Then rename the boundary as region. Okay. Now we will assign boundary at the edge of this region rectangle. For that, change the selection mode from object to edge. Then select 4 edges. Select the first edge, press Ctrl, second edge, third edge, and fourth edge. Then right click, assign boundary, then balloon boundary. Click here on balloon boundary. It is name is balloon 1. Press OK. Boundary is created as balloon boundary. Click on the balloon 1. See, it is shown in dark blue, so the boundary is created. Now in this simulation we will simulate the transformer with interleaved winding. So first I will name the windings. Suppose, okay, we need to change the selection from edge to object. Then only we can select objects. First this winding and this winding I am selecting, and in name tab I am written primary, primary. So these are primary. The all other three are secondary. Suppose for convenience I am creating primary is of red color and the secondaries are of blue color. So the red are primary and the blue are secondary, so it is a interleaved winding. Now in primary winding we will assign current. Select the primary winding, right click, assign excitation, current. So in the name write primary value is I am giving as 12 ampere solid and negative. Press OK. You can see here in excitation tab primary 1 and primary 2 has been created. Then select all the secondary windings, right click, assign excitation, current, name here as ACCONDRY. Secondary value 8 ampere, maybe 8 ampere solid positive. Okay, so the three secondary currents has been assigned. So excitation has been done. Now we have to apply mesh. First select core, right click, assign mesh operation, inside selection, length based. Then name as core, set maximum element length as 2 millimeter. Press OK. See, under the mesh tab core is created. Now select all the windings from here, right click, assign mesh operation, inside selection, length based. Name as winding, set maximum length. As the windings are very thin, so we need fine meshing for better result. So we will do zero point 0.2 millimeter of maximum element length of the mesh. Press OK. Under mesh core and windings meshing are created. Then we will set up the analysis. So right uh, right click on it, then add solution setup, then number of maximum process is 10%, error give us 5%. Yes, after last pass it's okay. Then convergence tab, yes, it is 5, all other okay. Solver, here it is 60 hertz, make it 150 kilohertz. Okay, then yeah, all other okay. Okay, press OK. So you can see here setup has been created, solution setup. Okay, now we maybe run the simulation. Just once press save. So for running, go to Maxwell 2D. First validation check. Okay, all are okay. Here you can see one yellow mark, exclamation mark in boundaries and excitation, but no issue about that. But all others are green tick, so it is okay. Then Maxwell 2D, analyze all. You can see here the progress. This is the message box and this is the progress box. It will take some time. Okay, the simulation is completed. Now we can see the results. Suppose um, here we want to plot the flux density. Now for that, press Ctrl A, right click, fields, B, mag B, all objects, done. You can see the flux density in all the code, and also it includes the region. If you want to change it, that is you want to see only the flux density in the windings, you can do that. Go here go expand this field overlays, expand this B, right click on mag B1, deselect the plot visibility, then select only the windings, right click, fields, B, mag B. Here all objects, done. You can see here only the flux density plot in the chosen objects, that means the windings. You can see the flux densities are higher at the outside, and it is getting lower through the inside. Now also you can see the flux line plot. So Control A, right click, field, A, flux lines, all objects, done. You can see the flux lines plots here. Suppose you want to uh, see flux lines very finely, then double click on this color palette. This window will show up. Then go to scale. Here number of divisions, it is 15. By default you make it 100. Then apply, close it. You can see the flux lines very finely. So then also expand here, disable the plot visibility. So the solutions are there, but those are not visible now. Now if you want to see the losses in the windings, right click on result, go to solution data, and here loss is already selected. You can see total solid loss in all the windings is 1.0234 watt here. Now if you want to note that what are the individual losses in each windings, you can also do that. For that, right click on the field overlays, then this calculator. Now here click on this quantity, scroll down, select ohmic loss, then click on geometry. Suppose you want to uh, know the solid loss in the winding named as primary. So select primary, press OK. Then here click on integration sign. So integrate, then eval, that means evaluate. Click here. See, it is shown here as 0.2523 something more. So this is the solid loss in primary winding. Primary winding means one of this red winding. If you want to, by this way, if you want to see all the loss in all the individual winding, procedure is same. Here, make sure here the volume is selected. Primary one, OK, integrate eval. Then quantity, ohmic loss, geometry, secondary, OK, integration eval. Quantity, ohmic loss, geometry, secondary one, OK, integration eval. Quantity, ohmic loss, geometry, secondary 2, OK, integration eval. Now if you add up all these five winding losses, you will you will end up with this number, 1.0234. You can do that on your own. Now if you want to see the inductances here, you need to click on the matrix, but you can see no inductances are shown. For that you need to do one thing. Go here in parameters, right click here, then assign, then matrix. Now it is all five windings are shown here. Click here all include, then press OK. Now run the simulation once again. Go to Maxwell 2D, then analyze all. Simulation is running. It is completed. Now right click on result, then solution data. You can see matrix is given now. Now see here, the type of matrix is real Z and imaginary Z. These are showing real Z comma imaginary Z, and you can show here that it is a 5 cross 5 matrix, that is primary 1, primary 2, secondary 1, secondary 2, secondary 3 cross the same. But we want this thing, that's R comma L, that means resistance comma inductance. Now the unit of resistance is ohm, inductance unit is nanohenry. Make it microhenry maybe. Okay, yeah. So ohm, and ohm maybe milliohm. Yeah, milliohm and microhenry. Now you can see that it is a 5 cross 5 matrix, and it is showing the inductances uh, with the corresponding to the 5 windings, but we need the inductances in a 2 cross 2 matrix for only primary secondary. So that also we can do. For that we need to go here again, parameters, right click on matrix, then click on join in series. In the group name, you click here, you rename it here primary 1, sorry, primary, then select primary 1, primary 2, press OK. Then in reduced matrix 1, right click, join in series, rename it as secondary, Select secondary 1, secondary 2, secondary 3, click OK. Now again run the simulation once. Maxwell 2D, analyze all. Simulation is running. Then it is complete. Simulation is complete. Right click on result, go to solution data. You can see in the reduce matrix tab it is showing original. Then click on reduce matrix 1. You can see here primary, secondary, primary, secondary. It is a 2 cross 2 matrix which is shown here that R comma L, that means resistance comma inductance. That resistance is milliohm and inductance is in microhenry. So these are all the things. You can explore some more things here. You need to nurture these things on yourself. If you face any issue regarding that, you can contact me. Thank you.